In today's video, we will be talking about the convex mirror equation. And after watching this video, you should be able to determine the image characteristics of a convex mirror and be able to use the mirror equation for convex mirrors. So let's get right into what we need to talk about. Few characteristics for convex mirrors, and had same type of list for concave mirrors, and this is just not a bad list to have either memorized or written down on your note card for tests, but basically you should know that convex mirrors will always produce an image that has the following characteristics. All right, it'll be located behind the convex mirror. Okay, that's part one. It'll never be in front of the mirror. It'll always be located behind, and because it's behind, it's what's called a virtual image. All right, it'll always produce a virtual image. The image will always also be upright. Okay, it'll never be inverted. It'll always be upright, and it will be reduced in size. So it'll be smaller than the object itself. Okay, so those are just kind of things to keep in mind. So as you're doing calculations, if you're getting things like real images or images that are bigger than the original object, you probably can say, hey, I'm doing something wrong here, and make the appropriate corrections. All right. So in the previous lesson, we talked about how to draw ray diagrams for convex mirrors, and those things are wonderful, but it does not give you a numerical value for the image formed. And so we are left with this question: what do we do? Okay, what do we do? Well, just like with concave mirrors, we can use equations basically to get a numerical value for the images produced off of these mirrors. So this equation is really no different than the concave mirror equation. Here it is in all its glory. The mirror equation expresses a quantitative relationship between the object distance, which is represented by d sub o, the image distance, which is represented by d sub I, and the focal length, which is represented by an f. And the equation is stated as follows: 1 over f equals 1 over d sub o plus 1 over d sub I. Okay, so this equation is something worth writing down because we will definitely use it again and again. Okay. Now, what if you want to know, like if I have an object, how big or small is that object, or the image, I should say, produced from that object? Okay, and so we're again going to use this thing called the magnification equation, which basically relates the ratio of the image distance and object distance to the ratio of the image height and the object height. Okay, and image height is h sub I, and object height is h sub o. And d sub I is the distance to the image, and d sub o is the distance to the object. And you'll notice there is a negative sign there, so make sure you don't forget that, because signs are pretty important in these equations. Okay, negative signs tell you different things about objects. Okay? And in this case, this negative sign is saying that it's a virtual image. Okay, so we'll talk more about that when we get to example problems. Okay, so let's do an example problem, shall we? It says a light bulb is placed a distance of 35.5 centimeters from a convex mirror having a focal length of negative 12.2 centimeters. Determine the image distance and the image size. Okay, the image distance is going to be just basically this. Okay. We'll draw ourselves a picture. I always recommend doing that. Okay, draw our principal axis. Here is our focal length. Okay, and it says it has a focal length of from this mirror to this F. This is 12.2 centimeters. Okay, and it's a negative because it's behind the mirror. Okay, so that's why that number is negative. So then let's see here. A light bulb is placed a distance of 35.5 centimeters, and so I'm going to just make my light bulb be an arrow. Okay, so this guy is from here to there 35.5 centimeters. That's centimeters. Okay. And that is actually our DO. Okay, that's our object distance. Okay, the question is, what is the image distance, right? What is our DI? Okay, well, what is that? Well, we're going to again want to use the the convex mirror equation. Okay, so that's going to be 1 over f equals 1 over dO plus 1 over di. Okay? And so 1 over f is 1 over 12.2 centimeters, and that's negative, equals 1 over dO, which is 35.5 centimeters, plus 1 over di, which is what we're trying to find out. Okay. And basically, if you do the algebra here, you would find that your di is negative 9.08 centimeters. Okay. And if you have a negative di, this is basically saying that the image is virtual, which means it's going to be on the right side of this mirror. Okay, it's going to be produced somewhere over here. Okay, it's not going to be produced on this side, on the left side. It's going to be produced on the right side. Okay. Now, for the image size, I actually cut off a piece to this. I was supposed to tell you that this light bulb is 4 centimeters tall. Okay, so that is the height of the object. Okay, so I'm going to make this screen black, and we will use our magnification equation. All right, and I'm going to have I have the numbers written down in front of me, so forgive me for not having enough space to do it on that page. But magnification is hi over ho, height of the object over the height of the image. Okay, is equal to negative di over do. Okay, so what do we know about this? Well, if we put down our information from the previous slide, we know that h sub o is 4 centimeters. We know that the di is negative 9.08 centimeters. And we know that the distance for the object was 35.5 centimeters. Okay? So I'm basically going to plug numbers into this portion of the equation and solve for hi. That's what I want to know. What is the height of the image? Okay. So let's throw those numbers in there, shall we? So we have hi over 4 centimeters is equal to negative, di, is negative. Oh, so this is negative, and this number is negative, so this actually becomes a positive. 9.08 centimeters. And I did that kind of fast, but there is a negative in the equation. There it is. And we have a negative di, so 2 negatives, this becomes a positive. Okay? And then my do is 35.5 centimeters. And basically, if you do this math, if you cross multiply and then divide, you should find an hi of 1.02 centimeters. Okay, so that's going to be the height of the image. Okay, so the object's 4 centimeters, the height of the image is 1.02 centimeters. Now, did we break any of our convex mirror rules? The answer is no, right? Because one of the rules is that the image is virtual, which there it is, it's negative, so it's a virtual image. Another rule is that the height of the image is going to be smaller than the height of the object. Is that true? Yes, it is. Okay, so these numbers look good. They're making sense. They're following the rules of a convex mirror. Okay, and this is kind of where you kind of check your work and make sure things are going correctly. Let's do one more example problem together. It says a convex mirror has a focal length of negative 10.8 centimeters. An object is placed 32.7 centimeters from the mirror's surface. Determine the image distance. Okay, cool. So let's draw a principal axis and a convex mirror. All right. So let's place an object. There it is. 32.7 centimeters from this mirror. All right, centimeters. And this would be our DO. Okay. And it says it has a focal length of, this will be our focal length, of 10, well, negative 10.8 centimeters. Okay, so how can I find DI, right? What is the distance to this image? Well, let's, bust out that equation. 1 over F equals 1 over dO plus 1 over di. Okay? And we're basically looking for this, 1 over di, right? So let's just plug in some numbers. 1 over 10.8 centimeters, and this value is negative, equals 1 over 32.7 centimeters plus 1 over di. So we're looking for di, and basically if you do that math and you just basically do the algebra, you find a distance to the image of negative 8.12 centimeters. Right, and that would be your answer. And this is making sense because that negative means it's virtual, so it's going to be somewhere on this right-hand side over here. It's 8.12 centimeters from the mirror. Okay, so things are looking good. If you're still confused in this, do not worry. We'll do a lot of example problems in class, but that actually takes care of this video. I will see you guys next time.